Dear students, in this video, we will study about the torque on a current loop which is placed in a magnetic field, then moving coil galvanometer, its principal construction and working, the figure of merit of a galvanometer, then sensitivity of a galvanometer, the current sensitivity and the voltage sensitivity of a galvanometer. Now let us study about the torque on a current loop. The force on a current carrying wire in a magnetic field is responsible for the motor operation. The torque on a current loop placed in a magnetic field. For this, let us consider a rectangular loop like this, PQRS, carrying current I, is placed in a uniform magnetic field B. Let A and B be the length and breadth of the rectangular loop respectively. The unit vector N, normal to the plane of the loop, makes an angle theta with the magnetic field, as shown in this diagram. The magnitude of the magnetic force acting on the current carrying arm PQ is given by the expression FPQ equal to IAB sin pi by 2, thus given by IAB. The direction of the force is found using right-hand corkscrew rule, and its direction is upwards. Next, considering the arm QR, the magnitude of the force on that is given by FQR equal to IBB sin pi by 2 minus theta, thus given by IBB cos theta, and its direction is as shown in this diagram. Next, we will consider the arm RS. The magnitude of the force acting on the arm RS is given by FRS is equal to IAB sin pi by 2, thus given by IAB, and its direction is downwards. The magnitude of the force acting on the arm SP is given by FSP equal to IBB sin pi by 2 plus theta, thus equal to IBB cos theta, and its direction is as shown. Since the forces FQR and FSP are equal, opposite and collinear, they will cancel each other, but the forces FPQ and FRS, which are equal in magnitude and opposite in direction, are not acting along the same straight line. Therefore, FPQ and FRS constantly coupled, which exerts a torque on the loop like this. This is the current loop having a current I, and there are two forces FPQ and FRS acting in the opposite direction having equal magnitude. The magnitude of the torque acting on the arm PQ about AB is given by tau PQ equal to B by 2 sin theta IAB, and it points in the direction of AB. The magnitude of the torque acting on the arm RS about AB is given by tau RS equal to B by 2 sin theta IAB, and also points in the same direction AB as shown in the diagram. The total torque acting on the entire loop about an axis AB is given by the expression tau equal to IAB sin theta B, so tau equal to IAB sin theta along the direction of AB. So in vector form, this can be written as tau equal to IA cos B. The above equation can also be written in terms of magnetic dipole moment, tau equal to PM in cross B, where PM equal to IA. The tendency of the torque is to rotate the loop so as to align its normal vector with the direction of the magnetic field. If there are n turns in the rectangular loop, then the torque is given by tau equal to NIAB sin theta. Now we will consider the special cases. First one, when theta equal to 90 degrees, or the plane of the loop is parallel to the magnetic field, the torque on the current loop is maximum. Therefore, tau maximum is written as IAB. Next case, when theta is equal to 0 degree or 180 degree, or the plane of the loop is perpendicular to the magnetic field, the torque on the current loop is 0. Next, we will consider about a device called moving coil galvanometer. What is a moving coil galvanometer? It is a device which is used to detect the flow of current in an electrical circuit. What is the principle on which it works? That is, when a current carrying loop is placed in a uniform magnetic field, it experiences a torque. Now let us see about its construction. The moving coil galvanometer consists of a rectangular coil PQRS of insulated thin copper wire. The coil contains a large number of turns wound over a light metallic frame. A cylindrical soft iron core is placed symmetrically inside the coil. The rectangular coil is suspended freely between two pole pieces of a horseshoe magnet. The upper end of the rectangular coil is attached to one end of a fine strip of phosphor bronze, and the lower end of the coil is connected to a hairspring which is also made up of phosphor bronze. In a fine suspension strip, a small plane mirror is also attached in order to measure the deflection of the coil with the help of a lamp and scale arrangement. The other end of the mirror is connected to a torsion head. In order to pass electric current through the galvanometer, the suspension strip and the spring are connected to the terminals like this. So here is the lamp and scale arrangement. Here is a lamp, here is the scale, and this is the moving coil. There is a mirror placed here, and the light will get reflected from the mirror and it will be seen on the scale so that we can measure the deflection made in the moving coil. Now the working of this moving coil galvanometer. Consider a single turn of the rectangular coil PQRS whose length is L and breadth is B. So PQ equal to RS and S equal to L, the length, and QR equal to SP equal to B, that's the breadth of the coil. Let I be the electric current flowing through the rectangular coil PQRS as shown. The horseshoe magnet has hemispherical magnetic poles which produces a radial magnetic field. Due to this radial field, the sides QR and SP are always parallel to the magnetic field B and experience no force. The sides PQ and RS are always perpendicular to the magnetic field and experience equal forces in opposite directions. Due to this, there will be a torque. For single turn, the reflecting torque is given by tau equal to B into F, that's equal to B into BIL, that's equal to IB into LB into BI, that's equal to ABI. Since the area of the coil is given by A equal to LB, we will get this expression. For a coil with n number of turns, we can write the equation as tau equal to NABI. So if there are n number of turns, this is the coil. The forces will be acting in the upward direction and also in the downward direction, thereby producing a torque. Due to this deflecting torque, the coil gets twisted and restoring torque is developed. This restoring torque is also called as the restoring couple. Since the moment of the restoring torque is proportional to the amount of twist theta, therefore we can write tau equal to k times theta, where k is the restoring couple per unit twist. And at equilibrium, the deflecting couple must be equal to the restoring couple. So we can get NABI equal to k theta, from which we can calculate the value of current I, which is equal to k theta by NAB, or I equal to G times theta. That is, G is equal to k by NAB, and that is called as the galvanometer constant or current reduction factor of the galvanometer. Since a suspended moving coil galvanometer is very sensitive, we have to handle with high care while doing the experiments with this apparatus. Most of the galvanometer we use are pointed type moving coil galvanometer. Then what is the figure of merit of a galvanometer? It is defined as the current required to produce a deflection of one scale division in the galvanometer. Next we will see what is the sensitivity of a galvanometer. The galvanometer is said to be sensitive if it shows large scale deflection even for a small current passed through it or a small voltage applied across it. Now let us see what is current sensitivity of a galvanometer. It is defined as the deflection produced per unit current flowing through a galvanometer, and it is given by the expression Is equal to theta by I, that's equal to NAB by K. So Is equal to 1 by G. Current sensitivity of a galvanometer can be increased by increasing the number of turns N, increasing the magnetic induction B, increasing the area of the coil A, and decreasing the couple per unit twist of the suspension wire K. Why we are using phosphor bronze wire? That is used as the suspension wire because the couple per unit twist is very small for phosphor bronze. Now let us see what is voltage sensitivity and how we can define. It is defined as the deflection produced per unit voltage applied across the galvanometer. So Vs can be written as theta by V. So V is equal to theta by IRG. This is by Ohm's law, and that's equal to NAB by K times RG. Or we can also write it as V is equal to 1 by G RG. That's equal to IS by RG, where this RG is called the resistance of the galvanometer.